Okay, we're going to go ahead and look at lesson 9.1. All right, this is when stuff starts getting real. Now, this chapter 9, unit 9, on College Board, they call this unit 10, so I have my unit 9 and 10 flipped. But this unit is going to be all about sequences and series. So we're going to start off talking about a few little examples that you may or may not have already learned in a previous class. Okay, you guys, factorials. Factorials are where you take, I'll give you an example here, a number, and it means that you multiply 5, 4, 3, 1. Okay? This comes up a lot in this section, so they're just kind of like defining that for you. If it's n, it goes n minus 1, n minus 2, n minus 3, dot, 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 down to 1, because we don't know how many terms there are. All right? So here's a problem they gave us. Simplify n plus 2 factorial over n factorial. Well, if n plus 2 is my first number, the next number down subtracts 1 from that. So it's n plus 1. The next number down subtracts 1 from that. So that's n minus 1, all the way down to 1. This one, it starts at n, and the next number down is n minus 1, n minus 2, all the way down to 1. Well, what you should notice is like 1, 2, all these things are going to cancel out up to here. And so, now depending on how much they want this simplified, I mean, I can just say it's n plus 2, n plus 1, and I'm probably going to stop there. You could FOIL it out, but it's not that important. Okay. When we talk about a series, this is a good definition. A series is a sum of numbers. So we usually say, the words that you'll hear in like pre-calc is sequences and series. Now the difference is a sequence is just a list of numbers, whereas a series is a sum of that sequence, okay? So that's the difference between when you hear people talk about sequences and series, right? A series is a sum of numbers. An infinite series, now check this out. We've seen this before when we were writing like Riemann sum notation. That is a Greek letter. It's capital letter sigma. Hey, sigma. Okay, and it goes up to infinity. So that means it's a1 plus a2 plus a3 up to an, and then it keeps going. Now this is important. Whenever something goes up to infinity, we have to put plus dot dot dot. Very important to include that. Okay? So like you'll notice on some of these examples where they have plus dot dot dot, that means these are like infinite ones, okay, as opposed to ones that stop. Alright, write out the first 5 terms of this series. So this would be starting at, okay, we're going to start right down here at n equals 1. So it's 1 over 1 plus 1, and then it's 2 over 2 plus 1, and then it's 3 over 3 plus 1, and then it's 4 over 4 plus 1, and then it's 5 over 5 plus 1. Those are the first 5 terms of the series. Okay? Okay, now you want to be able to write out series, and then you also want to take series that are written out, and you want to bring them back in and be able to like write an expression form. So we're going to talk about how to do that. Okay, so this first one, obviously it's infinite. So we're going to go n equals 1 to infinity. Now sometimes there's a different rule on the top than there is on the bottom. Okay, and you notice the top is just 1, 1, 1, 1, 1. Right? And sometimes it's easier to like write that fraction as like 1 over 1 so you can see what's happening. The top stays consistent on this one. It's just 1 every time. And then the bottom, if you recognize those are our perfect squares. Now, once I write my expression, I usually like test it to make sure it's right. So on my first term, it's 1 over 1. On my second term, it's 1 over 2 squared. On my third term, it's 1 over 3 squared. So I can tell that I got them lined up okay. All right. Okay, let's see here. N equals 1 to infinity. Okay, obviously the top is just 3, and then now I got to figure out what the bottom is. This is a little hard. This is a little difficult. Okay, let me talk to you about different ways. If you can't see right off the bat what's going on, different things you can try. So first you try adding. What is it, like 18 plus 96? So that obviously is not helpful, right? That's not doing anything for me. Let me try multiplying. Times 2, times 3, that's times 4, that's times 5. Well, when you're multiplying, but the number increases by 1 every time, hopefully you'll remember, like, okay, so that means that the first term is 1, and then it's 1 times 2, and then it's that 1 times 2 times 1 times 2 times 3, and then it's 1 times 2 times 3 times 4. And hopefully you guys will recognize these numbers pretty soon by the end of the chapter, because we use factorials a lot. You'll know your first few factorials. That's 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial. You can do those on, decimals or whatever. So like 5. The factorial button might be under functions. You're going to scroll like down a little bit. But if you're, using your, oh, it's not. It's actually just probably on my keyboard. There it is. So like it'll tell you, 5 factorial is 120. Okay. 4 factorial is 24. Something interesting about factorials is they're the fastest growing things. They grow faster than exponentials even. So even by the time you get up to, like, let's say 50 factorial, I mean, it's already like 10 to the 64. That means there's 64 decimals behind it, or 64 numbers, not even decimals, or 100. If you do this on your graphing calculator, it like crashes out. It doesn't like that. Even that 1,000 factorial, we can't define it. But an exponential, like e to the 1,000, that's too big also, because exponentials grow pretty big pretty fast. So these are things that grow very quickly. Anyway, just wanted to talk to you about that on factorial. So, okay, 1 factorial, 2 factorial, 3 factorial. So that's my equation there. All right, let's look at what next question. Oh, I didn't read the directions. Here's a great lesson on reading the directions. Write an expression for the nth term. I shouldn't have actually written these yet as series. The nth term on this is just 1 over n squared. And the nth term on this is just 3 over n factorial. So the nth term is just like what it would be if you, like what that term would be. Okay, now it's asking write an expression using sigma notation, okay? So now is when we go n equals 1 to infinity. And we got to look. Okay, again, I'm going to look at the top and bottom separately. The top, you might be like, oh, those are evens. That just multiplies by 2 every time. Okay? So, let's see. It's 2 times 1, 2 times 2, 2 times 3, 2 times 4. So that's just going to be 2n on the top. Okay, on the bottom, 1, 3, 5, 7, those are odd numbers. I did this wrong on the top. I said it multiplies by 2 every time. It doesn't. Adds by 2 every time. I'm like tripping. Okay. But when you add by 2, you're multiplying by 2 right here. Something that can be a little tricky. But like, these things make linear equations. And the slope is actually the number it adds by. Because if you think about it, the point, it goes like up 2 over 1, up 2 over 1. So 2 is actually the slope. The way that you generate odd numbers is you go 2n, but you go plus 1, so you start at 1. And then you guys can like test it, and, like look at it and see, is my first term 2 over, oh, I did it wrong. Odd numbers can be 2n plus 1, but that's if you start at 0. Now this is a good point as to why you test it, because I just went to test it, but my first term was 2 over 3, and that's 2 over 1. Odd numbers can also be generated by 2n minus 1. So again, this is why I always check at the end. Now when I plug it in, I get 2 over 1. And then when I plug in n is 2, I get 4 over 3. So now I can see it. Okay? So yeah, even numbers, make a note of it. are 2n. Odd numbers can be like 2n plus 1 or 2n minus 1. Just kind of depends on where you start on that, okay? Okay, this is a little tricky. This one is going to be multiplying by something every time. Now first, can you guys see it's multiplying by 3? These are all like times 3. But because it's changing signs, this is called an alternating series. Alternating means it goes positive, negative, okay? And what that means is I'm actually multiplying by negative 3. Now, when you are, let me make a note here, adding the same number every time, it becomes linear, right? Like it's y equals mx plus b. When you are multiplying by the same number every time, it actually becomes exponential. And exponential functions are like that, a times b to the x. So it's, and okay, when you add by a number every time, like these added by 2 every time, the number you add by every time is your m, right? So if you're like adding by 3 every time, it's that, and then you just have to figure out what b is. When you're multiplying by a number every time, the number you're multiplying by every time is b. Okay? So knowing that I'm multiplying by negative 3, that means it's negative 3 to the n. We want to use n with these. And then I just have to like check it. Now, when I plug in 1, I get negative 3. When I plug in 2, I get 9. This is like kind of weird and it's like not really matching up. But if I, let me just, go over a little bit. Okay. When I plug in 3, I get 27. Now it's like kind of matching up. I get negative 27. You can see that the numbers I'm generating, it's just 2 times that. In fact, when I plug in 0, negative 3 to the 0 is 1. And then you can see that these are all multiplied by 2 of that. And so what that does is that means that, let me move this over a little bit, 2 is this number. Okay, now, they're still not totally matching up because 2 times negative 3 to the first is negative 6. 2 times negative 3 to the second is positive 18. 2 times negative 3 to the third is negative 54. But I'm missing that first number. There are 2 ways that you can deal with that, okay? One way you can deal with that is you can say, well, I'm going to just start at 0. Because then negative 3 to the 0 is that, and so it gives me that first term. So you are allowed to change the number you start with. But oftentimes, rather than changing the number we start with, we still start with 1. We just say, well, how do I make that go to 0? And you make it go by going n minus 1. Because then 1 minus 1 is 0, and that generates my first term now, and my first term is 2. Okay, so again, there's 2 ways to fix that. You either change that down here, or you change that up there. Alright, hopefully that makes sense. We'll be practicing a lot of these. Okay, what happens if we add more and more terms of a series like this? Show a sequence of partial sums. Okay, so when n equals 1, the sum is 1. When n equals 2, the sum is 1 plus 3 is 4. When n equals 3, the sum is 9. When n equals 4, the sum is 16. Okay? Now, notice this word sequence. Sequence has commas in it, not pluses in it. That's like the biggest difference. And then the sequence will end up approaching infinity. Now, do you guys see that what this sequence is approaching? These numbers are all perfect squares. Which is actually kind of interesting that if you add odd numbers, you end up getting perfect squares. Okay? Kind of cool. Okay, I'm going to introduce you a few more vocabulary words. This sequence, when we start adding up the numbers, this series, it starts definitely approaching infinity, right? This is going to keep getting bigger and bigger and bigger. This is a word that we use here. We may have used this word once before, I'm not sure. Yeah, I think we did when we were talking about improper integrals. This series is divergent. Divergent means it keeps getting bigger and bigger and bigger, and we can't like narrow it down to a specific number. Okay? Now, let's look at this next one. Before I can do the partial sums, I need to like list it out, okay? So this is 3 over 10, 3 over 100, 3 over 1,000, 3 over 10,000, dot, right? Now, here's a notation for you. S of 1 means the sum of the first term. So the first term is 3/10. I'm actually going to write this as like 0.3 because I think you guys will see it better. Okay, my second term, the sum of the first two terms. Now this is 0.3 and this is 0.03. If I add them together, I get 0.33. My sum of the first three terms, this is 0.003. So when I add those, I get 0.333. My sum of the first four terms, this is 0.0003, is 0.3333. Can we tell what the infinite sum is approaching? If we keep on doing this forever, you guys, out to infinity, let's say, is it not just going to generate the fraction 1/3? Okay? So this is a convergent geometric series because it converged to a specific number, 1/3. So all the sums, if I add them up, are 1/3. Okay? Okay, a little bit more on some series stuff. We're going to talk about, there's two types. There's arithmetic and geometric. All right. We do not deal very much with an arithmetic series. I'll just like write a little note down here for you guys. We just don't really do that much. An arithmetic series is like, let's say I start at 3 and I add 4 every time. Right? So you can tell it's arithmetic because I'm adding the same number every time. And I told you guys that the way that you write an equation for that is the number you add every time is the slope, and it's a linear equation. So this is like 4n plus something, and then how do you find the something? Well, you just match up the terms. If n is 1, I want it to be 3. That's minus 1. If n is 2, I want it to be 7, and that works because 8 minus 1 is 7. Okay, that's arithmetic. We may do a few of those on the homework, but past this section, we don't really use arithmetic series very much. We just like don't care. Okay. More importantly is geometric. Now, a geometric series here's another vocab word, something called a common ratio. The ratio is what it gets multiplied every time. So remember how I told you, I was talking about up here, exponential equations are a times b to the x, right? Linear equations is mx plus b. Well, a times b to the x, does that not just look exactly like a times b to the x? I'm just changing x to n, and I'm changing b to r, because r is the common ratio. Now, notice also it's starting at 0, so r to the 0 is 1, so that gives me a, and then I multiply this times r, I should put a dot, not an x, times r, and I get ar. I multiply it by r again, and I get ar squared, right? And you just keep like multiplying by r. So the number that you multiply, that's called the common ratio, and that's what it generates. It generates a nice geometric series for us, okay? Where it eventually goes a, which was our starting point, and then r to the n, because we multiply by r a bunch of times. All right? Okay. If the geometric series converges, it's possible to find the sum, even if it has infinitely many terms. We did that up here. It had infinitely many terms, and we still were able to get it to go to 1/3, because it's like 0.333, and it goes on forever. All right? And I'm going to show you guys like how we can do that. Okay, so if this is kind of a proof, this is like a little bit tricky, but let's say the sum is a times r, a times r squared, a times r is a third, right? then r times that sum is, look, it becomes, okay, I'm going to try RA and then a squared and then third and then fourth. So we're just kind of like shifting it. So it's AR, and then if we shift it, it's AR squared. And then if we shift it, it's AR to the third, like that. And then if we shift it, it's AR to the fourth. Okay, I'm going to like erase this. Which if you, I'll write that plus better. Which if you look at that, that is just the first thing without the A, right? Which means that if I now take this first series, which is S, and I subtract that series, which is RS, the only thing that's going to be left is A. Okay? You guys get that? Okay. Then, with that, actually, I want to do some. Okay. Factor out an S. S times 1 minus R is A. And we get this formula. Alright, you guys, and here's the formula. S equals A over 1 minus R. Okay, that's an important formula. This is the formula for the sum of an infinite geometric series. Okay? And, you know, if you had taken a pre-calc class that had sequences of series in it, you would like learn about all these formulas and stuff, and this is one. You know, you can write S infinity, but we usually don't. We just distinguish if it's a partial sum, we call it like S1, S2, S3, but just S means all of the terms, okay? Now, A, and usually when I see this, I write like A1, that's just the way I'm used to doing it. A, or A1, is the first term, and R is the common ratio, okay? Let's go back and see if it's going to work with this question we did, because this one, you know, was an infinite series. Okay, so the formula said I just do A1 over 1 minus R. Okay, A1 is actually right here. That's my first term. So my first term was 3 over 10. Now, can you guys tell, I was just writing these as decimals, let me just get rid of the decimals for a minute, what it's multiplying by every time? 3/10 multiplies by what to get 3 100ths? 1/10, right? And then I multiply by 1/10, and I multiply by 1/10. Okay? So R is 1/10. And if I'm going to simplify this, 3/10 over 1 is 10/10. 10/10 minus 1/10 is 9/10. When you divide fractions, it's like multiplying by the reciprocal. And so I get 3/9, which is 1/3, which is so cool because I got that up there. So that's the way that you can show with the formula that it converges to 1/3 when you add all the terms up to infinity. Okay? Now, in order for this to work, all right, it has to be a divergent sequence. Now look, in my head, I picture divergent like that. That's just how I picture it. Okay, it's like, it's going down like that. I picture like a funnel. I picture a convergence sequence like that, either just infinitely big or like infinitely small, you know, but it's like growing. So again, that's just kind of how I picture it, okay? Well, a divergent series is when R is bigger than 1. Because if it's bigger than 1, like if R is 2, it's getting bigger and bigger and bigger. If R is 3, it's getting bigger and bigger and bigger, even faster. The convergent series is when R is less than 1. Now, in terms of like negatives, it's the same thing, but like think opposite. A divergent series is when r is like less than -1, meaning -2, -3, -4. It's just negative, but it still blows up like that. And a convergent series is when it's bigger than -1. Okay? There's two types of series we don't really talk about. And that is r equals 0 because it would end like that. Right? Let's say I have a series 3, I start at 3 and r is 0. It's like already gone, okay? So that's just dumb. We don't talk about r equals 0, and we don't really talk about r equals 1 either, because let's say I had that series, okay, and I'm multiplying by 1. It's just 3, 3, 3, 3, 3, all right? Which actually, that one diverges because it gets bigger. Okay, so like, pretty easy way to say that, and I guess like, you know, when it does equal 0, I mean it converges, right? Because it converges to 3, even though it's kind of silly. We don't really mess with those very much, okay? Well, another way of writing basically what I wrote over there is this. This sum formula only works if the series converges. You need to remember that. And then if r is greater than or equal to 1, and we put absolute values on it, you guys, because it also works with negative numbers. But when I put an absolute value on it, it means as long as r is less than or equal to -1 or greater than or equal to +1, okay, it's going to diverge. So basically, if r is a number bigger than 1, right? If r is a number less than 1, it will converge. Now, here's how this works. Now, these first two questions are very interesting, okay? Number 9 and 10, they have a different r, so you got to be careful, because when I look at this, it looks like, oh, they're both 3/2. But you notice the first one only has an n on the bottom, and the second one has an n on the top. If you cannot see it right away, now you will get better at these, but if you can't see it right away, what I want you to do is write out the first like 3 or 4 terms, okay? When n is 0, that's 3/1. When n is 1, that's 3/2. When n is 2, that's 3/4. When n is 3, that's 3/8. Okay? And now I can see it. The 3 is not changing. The only thing that's changing is the bottom is multiplying by 2. The top is multiplying by 1. What that means is that r is 1/2. Okay? Now, you could have seen that by rewriting this in a different way. This is the same thing as if I wrote 3 times 1/2 to the n. Hopefully that makes sense to you. And the number in front helps determine our first term, and then the number on the inside is what we multiply by every time. Now, is that number less than 1? Less than 1. It is. So this series diverges. I mean, I'm so sorry, got that wrong. Converges. That's a good thing, right? That series converges. And it says, if possible, find the sum of the series. Okay, if it converges, I'm allowed to find the sum. So it goes like this. The infinite sum is, remember the formula, first term over 1 minus r. So here's my first term. My first term is 3 over 1 minus a half. Okay? You can put this in your calculator if you want. 1 minus a half is a half. And then 3 times 2, and I multiply by the reciprocal, is 6. So if I went out to infinity, and I was adding, I'll actually show you guys because this will be kind of cool. Okay, 3 plus, and then the second term was 3/2. 3/2 plus 3/4 plus 3/8 plus 3/16 plus 3/32. I actually get there pretty quick. Like, you can see where it's going within the first 10 terms, you know? Let me do like one more. But you guys see how it's getting like really, really close to 6? The next one would be 3/64, 128. You know? It's getting very, very close to 6. The next one will be 3/256. Right? I mean, we're like almost there. 3 over 512. And then that's all the power to 2 I know. But look, I'm at 5.9941. If you keep going, it'll eventually, it'll display 5.9999999. And we know that when that goes on forever, it goes to 6. So this series will sum to 6. Now, if I do this next one, let's say like you're not sure. This one's a little more obvious what R is. But let's say you're not sure, okay? And we're starting at 0. 3 halves to the 0 is 1. 3 halves to the 1 is 3 halves. 3 halves to the 2 is 9/4. 3 halves to the 3 is 27/8. So you can see what's happening here is that, the top is multiplying by 3 and the bottom is multiplying by 2. And the ratio is 3 over 2, which just comes from right there. Anyways, okay? 3 over 2 is bigger than 1, so this series diverges. It's going to get bigger and bigger and bigger the more terms I add. It's never going to like settle down. And it's just going to keep on growing. So we cannot find the sum. Okay? I'm just going to say can't find the infinite sum. Alright? Because it just keeps getting bigger. Okay, can you guys see R in this one? I can see it like right here. This one's a little bit different. Look, it's starting at 1. Be aware of that. So my first term is actually 4 times -1/2, which is -2. My second term is 4 times 1/4, which is 1. My third term is 4 times -1/8, so that's -1/2. Alright. So there's a couple of terms listed. And it's really easy to tell on this one that R is -1/2. Now remember, you can write it like this. That's a good way to do it, is less than 1. That's usually how we write it when we're proving it. And again, as long as R is less than 1, the series converges. And if the series converges, we can sum this all up. What do you guys think it's going to go to? So it's alternating, and it starts at -2 and then 1. So it goes -2 plus 1, -1/2. And then it would go to what? +1/4. Then it would go to -1/8. And then it would go to +1/16. Okay? So what is it going to do? Like -1.3? Let's see. Let's actually use our formula to sum it up. Now my sum is A1 over 1 minus R. A1 is first term. The first term is -2 over 1 minus R is -1/2. Okay, so R was negative in this one. That's 1 plus 1/2, which is 3/2. And then when I multiply by the reciprocal, I get a sum of -1/3. That looks like it's going to -1 1/3. Let me see what I messed up here. A1 over 1 minus R. Oh my gosh, that's crazy. I see what I already did, and hopefully you guys see it too. Luckily it was at the very end. The 2's do not cancel out. That's -4/3. And you guys, what is -4/3? It's -1.333. So I was exactly right. If I do another term or two of this, it's going to get really freaking close. Okay, and by the time I go to infinity, it goes to -1.3 repeating. Whew, that's just a silly error. You guys know how that goes. Okay, so this is really fun, actually. I kind of like this stuff. It like feels good in my brain when I do things like this. Find the fraction form of the repeating decimal, 0.080808. Right, you guys know that any repeating decimal can be changed into a fraction. You do it using calculus, so you do it using infinite series, and it goes like this. This is the same as 0.08 plus, and then I got to add the next one, plus, and then 1, 2, 3, 4, 5, 6, I think 1, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. Yeah, okay, perfect. Right? Okay, you guys, now with decimals, it's a tiny bit easier to actually see. This is 8 over 100. This is 8 over 4 decimals, so that's 1, 2, 3, 4. This is 8 over 1, 2, 3, 4, 5, 6, right? 1, 2, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 1, 2. I'm like tripping here. Okay, 2 zeros. Oh no, that was right. 4 zeros. 6 zeros. Whew. Okay. Now what you'll notice is, what am I multiplying by every time? The 8 is staying the same, but the bottom is going by 100 because this is like 2 decimal places. If it was only 1 decimal place repeating, like 0.7 repeating, it multiplies by, 10 on the bottom, just multiplying by 100 on the bottom, and the top is staying the same. So R is 1 over 100, and my first term is 0.08 or 8 over 100. And so you go like this. The sum is A1 over 1 minus R. So it's A1 over, and then 100 over 100 minus 1 over 100 is 99 over 100. And then you guys, when you multiply the reciprocal, what do I get? I'm really like not on my highest game here, because A1, but at least I caught it this time, A1 is 8 over 100. Yeah. Okay, sorry about that. A1 is 8 over 100. So when I do this, it ends up just becoming 8 over 99. And if you do, 8 over 99, you get 0.080808 repeating. Okay? So I can turn any repeating decimal into a fraction with an infinite sum. All right? Okay, next. This series does not converge. Show a sequence of partial sums. Okay, here we go. The first sum is just that, which is 2. The second sum, this is going to be a little bit easier for me if I do no, not decimal, it's not negative 1. That's 3 halves. That's 4/3. The next one would be 1 plus a fourth, which would be 5/4. Okay, the first sum is 2. The second sum is those added together. That's 4 halves, so that's 7 halves. The third partial sum is all 3 of those added together. I don't know what 7 halves plus 4/3 is, for goodness sake. 7 halves plus 4/3 is, push that button to make it a fraction, 29/6. Lovely. The fourth sum is all of those added up and adding 5/4 to it. So again, I'm just going to do that on my calculator, plus 5/4. And that sum is 73/12. Okay? This does not converge. It just keeps getting bigger and bigger and bigger every time. All right? Now, something I want you to note. This is not geometric. So like that R thing wouldn't even really work. It's because this is just like not geometric. Okay? We're not multiplying by a certain number every time. We're actually like adding a fraction every time. So it's not what we were just doing with the R's. All right? But I do know that this is getting bigger and bigger and bigger. Maybe I should have used this with decimals. Let's see. 73/12 is 6.083. 29/6 is 4.83. Okay, and so you can see that these partial sums are getting bigger, so this does not converge, right? A series cannot converge unless the terms approach 0. This is extremely important. So unless these go to 0, we can't converge. It's just going to keep getting bigger and bigger, all right? This is our first test. It's called the nth term test, okay? And what it says is, and we're going to learn like 10 different tests this unit. All right, there's a lot of tests. In fact, here's a little page in the back of our packet. Those are all the tests you're going to have to memorize. Oh, good, there's only 8. Okay, there's 8 tests. This is your first one. So you're going to have to memorize them. They're going to be introduced a little bit at a time. My first test is called the nth term test. And what it says is, if you take the limit as the terms approach infinity, if it does not equal 0, it diverges. Okay? Now, what's interesting is you would think that means, oh, if it equals 0, it converges. That's actually not true. If it equals 0, it's inconclusive and you have to try a different test. So this is an nth term test that we can only use to show divergence. We cannot use this to show convergence. It's just not allowed. So here's how you do it. Show that this diverges. Well, let me see what the nth term would be. And the nth term is just this as I approach infinity. Okay. Now, let me algebraically kind of simplify this, or at least like kind of show you what's going on over here. It's n minus 1, n minus 2, n minus 3, dot, 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 down to 1. And then, does that say 2n factorial? Okay. 2n factorial goes like this. And then it's like 2n minus 1, 2n minus 2, 2n minus 3, down to 1. Okay, now I can't really cross anything out, so this actually didn't really help that much. Oh, and it's like plus 1, plus 1, plus 1, right? So that kind of isn't really helping, but let's just think about this. Sometimes you're able to do it without showing the algebra, and you can just kind of think about it. As I approach to infinity, does it make sense to you that 1 is like negligible, like it's like, okay, plus 1? It's not going to really do anything. Like, think of 100 million billion plus 1. Kind of, it doesn't really matter. So it's very similar to when we were like comparing exponents and stuff. So this compares to that because the plus 1 isn't really going to do anything, and that the n factorials can cancel out, and it equals 1/2. Okay, so because 1/2 is not 0, we write that. We say because 1/2 is not 0, so that's how we know that we know the property. We say this. This series diverges by the nth term test. Now, I want you to get used to writing that out. I know it's going to be annoying, but I want you to write that out because once we get to the end of the chapter and we have 8 different tests, every single one you have to write, it converges by this test or it diverges by this test. This guy uses an abbreviation in his text, NTT. That is okay if you want to use that with me, but I would highly recommend on the AP test do not use abbreviations like that. They might not know what the heck NTT is, okay? So they might, be confused, so we would write out nth term test. All right? Okay, so looking at the assignment, there's some like simplifying, write the nth term, write the series. This is where this gets really, really important, okay? Let me kind of explain how you would do this first. This is the super important part of the assignment. Okay, if it's geometric, right? If you can find R, and the absolute value of R is greater than 1, it converges, and you can find the sum. That's the sum, okay? If the absolute value of R, just wrote those backwards, you guys. This is killing me. If R is small, it converges because it gets smaller. If R is big, it diverges. Just like writing my sums, right? And then you cannot find a sum. Now, not all of these are going to be geometric, though. So if it's not geometric, if it's other, you're going to try the nth term test. If it does not go to 0, we say it diverges. And then you stop because there's no sum. If it does go to 0, we don't know. It does not mean, if the nth term goes to 0, it does not mean that it converges. We just don't know. So you would write inconclusive. So there are two different types of problems in here, geometric ones and not geometric ones. If it's a geometric problem, okay, follow those rules. If it's a other, not geometric, follow those rules, okay? And then it just says, determine whether they converge or diverge. Show a justification in the name of the test being used. This test is just, it's a geometric series. It doesn't have a name. This test is nth term test. Nth term test shows it diverges. Find the sum if possible. This is the only one you can find the sum on. You can't find the sum on anything else. Only geometric that converge. Okay? All right. Good luck with that.